Okay, so this question is talking about how the electrons in iridium and its iridium 4 plus ion. It's asking how the electrons are laid out. So previously you've learned the model that, you have a nucleus, and then in the first you have these little electron shells, and each shell holds a different amount of electrons, right? And then each, basically the further down you go, you add one more of these shells. And then each shell, obviously because they're bigger, they can hold more and more electrons. Okay? We're basically taking that idea, but now people think of electrons in terms of orbitals. So instead of just existing in a simple ring, electrons don't actually look like that in real life. What they do look like, however, is that they exist in clouds. So instead of just having these simple rings, you have, and this is like, probably you don't have to know this, but I'm just explaining for context. Each of these orbitals, previously known as shells, have a better probability of existing in one area versus another. So this first shell that you see here, those electrons exist in a cloud. Pretend this is 3D, just simply like this. And then the next shell, I'll explain later, it's called a p orbital. Those electrons like to exist in like this figure 8 shape around iridium, right? And then this next shell has a different orbital like probability, and eventually just depending on the different energy levels, the electrons like to exist in different areas of the atom or ion, right? So this periodic table is kind of just outlining how many orbitals or how many shells each atom has. So hydrogen, for example, only has one electron, so its electrons are only going to occupy the 1s orbital. But for example, you have things like Mercury, which are way bigger. They have so many, it has 80 electrons, right? So it's going to be occupying the 1s, the 2s, the 3s, the 4s, all the 2p, 3p, because it's all the way down here, electrons are going to occupy all these different orbitals, plus the 5d is where it stops. Likewise, like xenon, it has the 1s, the 2p has everything before it, so it has the 3s, the 4p, the 3d, but it's going to stop at the 5p orbital, it all just depends on the atomic number, right? How many electrons your thing has. So in our case, we're dealing with iridium. So where is iridium? She's right here, okay? Number 77. So that means we're working with 77 electrons. So that's a lot of shells to fill out, right? That's a lot of orbitals that these electrons need to occupy. So we know that they're going to be somewhere in the 5d orbital. So we know they're going to occupy the s, the 2s, the 3s, 4s, 3d, 4p, 2p, all of that. And then it's going to end somewhere around the 5d orbital. Okay, so how is this going to relate to our question? So, yeah, I'm just ordering. This is the periodic table. This just helps you kind of visualize which elements use what orbitals. And down here, this is just a list of the order in which electrons take up space. So, for example, hydrogen uses the 1s. And let me explain this first. Oops. So yeah, this is just the order in which electrons fill up. So they'll first, because a hydrogen does not have a 60 orbital, right? It doesn't have enough Jeez. It does not have enough electrons to fill up. It only has one, right? So this is the order, this list is just the order in which electrons do fill up their orbitals. So they'll start with a 1s, 2s, 2p, 3s, 4p. Basically, I guess you have to memorize this. I doubt it. I don't know what your access to the internet or is whatever like, but yeah. And because our iridium is right here, it's going to occupy all of these and this, and then the 5D, it might be semi-full depending on how many electrons exist on it, and that's what we'll figure out, right? So, yeah, the bigger the atom is, the more electrons it has, and the higher orbitals their electrons will fill. And this is kind of just another, oh yeah, and all these orbitals have different energies, like our last question, right? The closer the orbital or shell is to the nucleus, the more stable it will be, the less energy it will have. And this is displayed here, but in a kind of a weird way. It's just kind of hard to wrap your head around sometimes. So you see the y-axis, we have increasing energy. This makes sense because, like I said, the 1s orbital kind of relates to the one right around the nucleus, right? That's the lowest in energy, which makes sense because, like, the closer you are, the negative electrons will be balanced by the positive nucleus. And then as you increase the size of your atom, you're going to introduce more and more and more orbitals. And these orbitals are going to be super big, and these electrons can exist super far away from the nucleus. So that's why the higher you go, and that's how we get this order. The order is basically from lowest energy to highest energy, which makes sense, you know, as an electron and just a law of the universe, things like to follow the path of least resistance. They like to be as low as energy. They like to be as stable as possible, especially electrons. And that's a huge thing of chemistry. Stability means what the chemical will look like, what it will react with, all of that stuff. So it makes sense that we get this list. We fill out the electrons here first, then we'll go here and here, you know? Electrons aren't going to like randomly fill up these 5D orbitals. Like I said, the hydrogen doesn't even have enough electrons in order to fill up those. So that's how we get this order. And the different numbers, the 1, 2, and 3, that's just, you can kind of see here, as you go further down, you introduce one more shell, right? That's the same thing. It's called the principal quantum number. You just introduce one more. It correlates to size, basically, which makes sense. You know, you go down 1, 2, 3. That makes sense. And then the S, P, D, and F. I don't really know what the order comes from, like why they get those letters from, but you don't have to know that. You just kind of have to know the order. So yeah, so first electrons will go fill up here, and this is how I guess I'll go into the next part. How many electrons? Because you can see here, this is 1 squared, p's have 3, what's going on here? Basically, s orbitals, you can kind of, all of them right here, they only have one box, or one line, whatever. Each box, or each line, can hold 2 electrons. So, hydrogen only having 1 electron. We like electrons, we use signs because, arrows, I mean. This is spin down, and this is spin up. Yeah, some people draw the full arrows, but I'm lazy and I just do that. Because basically, again, this is like some quantum chemistry or like whatever, I don't know. electrons, they spin different ways. We call one of them spin up and spin down. So a hydrogen only has one electron, so it'll be there. Helium has two electrons, right? So is it going to fill up a p orbital? No. It will fill up the s orbital because each, like I said, each box, each line can fit two. And again, we like the path of least resistance. Helium is not randomly going to have two electrons there. Like, that makes no sense, okay? Okay, yeah, so let's keep going. And then lithium, we can see it's in the 2s orbital. So that means its 1s orbital will be full, which makes sense. It has 3 electrons. We already got 1, 2, 3. Okay, moving on. Beryllium has 4 electrons. You can see it's still in the 2s lane, so that means its 1s will be full, which makes sense. 1, 2, 3. And here's where we get tricky. You could say, oh, 4. But apparently that does not exist. Instead, we put the 4th electron in this orbital. There are special rules, and that's just one of them. So basically, the rule is you spin, the spins have to be opposite in one box or in one line, one orbital, okay? Because we don't want 2 electrons with the same spin. Then you'll get some weird stuff going on, okay? So first you fill up in different direction, and then you fill up each line one at a time. So let's going on to boron, which has 5 electrons. So we'll have, oh shoot, I totally messed up. Sorry. So this is the 1s orbital. Yeah, I'm silly. See, I was filling up the p orbital for lithium, when lithium, really next we would go to the 2s orbital, so my bad. So yeah, lithium would be 1, 2, 3. And then beryllium having 4 electrons, same thing, 1, 2, 3, 4. Different spin. Okay, and then boron, 5 electrons, and this is how I know I messed up, because we're using the 2p orbitals now. Okay, and boron has 5 electrons, so again, spin up, spin down, 1, 2, 3, 4, 5. There we go. And then carbon, 6. Instead of putting it down there, no, we fill up the other orbitals first. So that would be carbon, 1, 2, 3, 4, 5, 6, good. Nitrogen, 7. There. Again, and then this would be wrong though. Let's go to nitrogen, which has 7. So we have 1, 2, 3, 4, 5, 6, 7. That's pointing down. That's no good. That's not how you fill them out. They all first fill up in the same direction. Okay, so 1, 2, 3, 4, 5, 6, 7. And then oxygen, 8. Where would that electron go? It would go here, but with a spin down, right? Because we like to fill each thing with opposite spin. Okay, and then the next one would be 4 and 9, spin down, and then the next one, neon, spin down. And what's after neon? Sodium, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So a little thing to help you so you don't have to count each time is like I said before, sodium is 3s. So it's 1s, 2s, and 2p will all be full. And it's just the 3s we need to count for. So using that logic, let's check it out. So it has 11 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. See, I could have just blindly filled up the rest and would have just been left with that 11th one. Okay, So again, I'm just using the atomic number, how many electrons, and then filling them up in a specific order, right? You can't just go from 1s to 2p like made a mistake. You have to go 1s, 2s, 2p, 3s, 3p. That's what this list is for. And again, the spins have to be opposite, and then you have to fill in all these lines, and then you can't just randomly fill them up. No, you can't double fill up. You have to fill up each line with one and then the opposite one by one. Okay? Okay. So now that you kind of see like the general pattern, we can start moving on. So yeah, s orbitals hold 2 electrons. P orbitals hold 6 electrons. D orbitals hold up to, I guess, because like we saw with sodium, it ended in the 3s, but it didn't fill up the 3s. So yeah, we can say 2, 4, 6, 8, 10. So hold up to 10 electrons, and then you get to your f orbitals, and they can hold up to 14. Okay? So, because we're dealing with super big iridium with 77 electrons, and it's in the 5D, so we know, and 5D is right here. So we know that all this will be full. So the 2 here, and then it's gonna be here, and then the 3s here, and yeah. So that can kind of save us a step. Because basically your answer, how it has like a million boxes? It's like type answer, ... type answer. Because in each box it wants you to put how many electrons are in the 1s, how many electrons are in the 2s. And obviously iridium is super huge. It's in the 5D orbital, so yeah, that's going to take a lot of typing. Okay, so now that we've had some practice drawing in each electrons, it's asking us for the electron configuration, which is basically the same thing, but in words, not arrows. You're, like I said, you have to type, and you can't just draw them in these boxes. So using this list, it gives us information. 2p3s. Okay, now basically the electron configuration lets us know A, which orbitals we're dealing with. Okay, easy enough, we wrote them down. And it also tells us how many electrons are in each respective orbital. So s orbitals, no matter if it's 1s or a 6s, they only hold 2 electrons each. So let's take an example. Let's use sodium, which has 11 electrons. And because we're smart, we're like, okay, the 1s, 2s, and 2p will be fill, and we're going to have to deal with the 3s eventually. But let's not get ahead of ourselves. Let's just understand that we're probably going to be ending up at the 3s. Okay? So, how do we let people know how many electrons are in the 1s orbital? We just put a little exponent, 2. Right? And how many will be in the 2s? Again, s orbitals can only hold 2 electrons. So we know that there's going to be 2 there. So right now we're at 1, 2, 3, 4. Okay, now let's move on to our 2p orbital. How many can those hold? They can hold up to 6. So let's see. 1, 2, 3, 4. Plus 6 would be 10. So that makes sense. So this 2p orbital holds all the 6. And remember, we know that because of its position on the periodic table. 3s though, is that full? We don't know. It could be not, but let's check. So right now we have 1, 2, 3, 4. We have 10 electrons used up, but a sodium has 11. So we know that the 3s will actually only be holding 1 electron, not 2. But for example, we go magnesium, which is right beside, which has 12 electrons. We know that it'll be same thing. The 1s is full, the 2s is full, the 2p is full, which means there's 6 there, and the 3s will be 2. And a way you can check is that just add up all of these exponents and it should equal your atomic number. So let's check that. So 2 plus 2 plus 6 plus 2, lo and behold, equals 12. And again, if we were to do that filling up, which I don't know if you will ever have to, but just to visualize it in terms of like increasing energy, remember, 12 electrons. So for magnesium it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, simple enough. So now let's get on to your example, which is iridium. So again, with our help, we know that it's going to be in the 5D. And that's only because we have our periodic table. But because I want you to learn, let's just pretend we didn't know it end in 5D. So we're going to go step by step by step. Okay. So, hold on. Okay. So again, we always start with the 1s orbital because that's the lowest one. That's the one where all the electrons will start. So for iridium, which has 77 electrons, we know that this will be full. Okay, and then I'm actually going to bring the list down or I'm just going to rewrite the list because I don't even remember it. So yeah. And there's 5D, but I'm just going to keep going because I wouldn't have known it stops at 5D. Okay, but 7P is really large, so usually I don't even know if things exist there. Anyway, okay, so let's start with 1s. We know that's going to be full. 1, 2, 3, 4. Again, we're going to 77 electrons, so this is going to be full because it has 6 electrons, and p orbitals hold 6 electrons. How many electrons do s orbitals hold? 2. How many electrons do 3p orbitals hold? 6. How about 4s? Again, no matter if it's 1s or 4s, they only hold 2 electrons. So, yeah, 4s, see, 2, 2, 2, 2. Always 2. And then D, oh, that's a new one. How many electrons do d orbitals hold? 10. Well, let's see how many do we have left to work with, because is it the full 10 or I don't know. So let's check. So 2, 4, 10, 12, 18, 20. So yeah, this is going to be full. So now we're at 20 electrons, or, right, 2, 4, oh my gosh, I'm so bad at math. 2, 4, 10, 12, 18, 20, plus 10, 30. So we have 40, did I just say, yeah, we have 47 more electrons to fill out. Okay. 6, because that's full. So now we only have 41 more electrons. S orbital, 2. we have 39 left. D orbital again. 10. So now we have 29. Jeez. P, they hold 6. So now we're at 23. S orbitals hold 2. So now that we're at 21. F orbitals, how many are those? 14. Yes, because we have 21 electrons left. We know that this will be full, so we can put 14 down. And what is 21 minus 14? 7. So we have 7 left. Okay, and like we predicted, we're left at the 5D. And how many d orbitals hold up to 10? But we only have 7 left. So there we go. That would be your electron configuration for iridium. So again, let's just go over. Looking at the periodic table, we know iridium has 77 electrons. And these electrons like to fill up each orbital consecutively, like in a specific order. And depending on if it's an S, P, D, or F orbital, that dictates how many each can hold. So S, 2, P, 6, D, up to 10, and F up to 14. So basically, you can do it however style you like. Like at the end, you kind of saw I was just subtracting after each one to see if I had enough to fill up the next one or not, right? So yeah, it's just a matter of counting. So yeah, your final answer, in the first box, I guess you would say 1s, 2. The next box, you would put 2s2, then 2p6, all the way until you got to 5d7. And yeah, these are like known. You can also, Google it if you want to double check. And just another thing, like if you do end up Googling it, you might find a different notation, which it's basically a shorthand, because nobody wants to write all this because they know that everything before that is full. So why would we want to write all this out when we know that the 1s to 3p is going to be full, right? So what people do is they take the nearest noble gas as kind of a landmark, because all these noble gases, why they're you've heard that noble gases are stable. It's because their outer shells or their outermost orbitals are always full. So basically you take the nearest noble gas and then you just fill in whatever's left. So for example, with iridium, our nearest noble gas is xenon. So what people do is that they'll say, okay, xenon plus, and then you pick up where it left off. So xenon, and then we go to the, where is xenon? Ends at the 5p. Sorry, I don't know if you can see. So you take your nearest noble gas, and you're like, okay, xenon ends at 5p. So what's after 5p? 5p, then we go to the 6s. So then we go 6s2, 4f14, 5d7. Okay. Yeah. Sorry, I'm just gonna... But yeah, because you have to type it all out, you're just gonna, like, type in all of this. But because you don't, like, your answers don't use exponents, they just want you to put 1s2 like that, so. Let me just double count on my own computer, 1 sec. Three D 4S 4B 5S 4D 5 6s. Okay, yeah. Okay, so, sorry it's kind of messy, but yeah, that's a answer for the iridium. Now, the next part of your question is asking the electron configuration for iridium 4+. Now, what does this 4+ mean? That means that we took our neutral iridium with its, iridium with a valence. Sorry, I need to bring up a periodic table. See how many valence electrons it has. Okay. Iridium has, just so I can draw. So it's going to be, I'm just drawing the outermost shell, okay? So pretend all the orbitals are still there, and I'm just drawing the outer one. So it has 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is neutral iridium, the thing we just drew the electron configuration for. Actually, no, that's going to confuse you, because why are there 9 electrons? So anyway, sorry, the 4+ just means we took away 4 electrons. Which makes sense because electrons are negatively charged, so if you're taking away these negative charges, you'll end up with a more positive substance, right? So, instead of having 77 electrons, we took away 4. Now we're going to have 73 electrons to work with. So, again, just go through the list. 1s, 2s, 2p. But because it's already here, I'm just gonna ... and look at the end. So this was for neutral iridium. But when we took away 4 electrons, we know that this number is wrong because we don't have 7 in the outside anymore because we took away 4. So 7 minus 4, that would be 3 electrons there. So instead of being 5d7, it would be 5d3. That would be the thing for IR4+. If they wanted to ask you for IR2+, we would be having 75 electrons, and then again you would go through the list, but I don't really want to do that, so you would just look at the end instead of having 7 electrons there because you took away the 2. And again, you always take away electrons from the outermost orbitals. Like, I wouldn't be taking 2 electrons away from the 2p6, no. That's way too stable. It would be take too much energy in order to bring those electrons away. So you always use the outside ones, so then it would be 5d5, for example, right? So yeah, just, I guess, don't make any typos when you type, and again, you can always double check. Honestly, let's double check by counting our exponents and seeing if it does add up to 77. So we'll go, I'm just going to put in my calculator, 2 plus 2 plus 6, or I can just, honestly, let me just count in my head, or out loud. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 48 plus 6, that's 54, 56, 77. There we go. And yeah, the order of the letters matter. You can just Google them, like electron configuration order. Okay, that's that. Sorry, I'm tired. I don't know if I made sense in this one.